Okay, let's start. Good morning, welcome back. I hope your break was good. I've been debating on whether or not I should say what I'm going to say now, and I decided to say it. So over the weekend, over the break, I learned that my uncle passed, and I was close to him. And so part of my mental capacity is sort of like going to that, handling that death right now. The debate was that whether or not I should even mention this being sort of like a personal matter. But I guess part of this class is, mathematical maturity. And I think part of mathematical maturity is the understanding that mathematics is a human endeavor. Mathematicians, these people that we read in books and stuff, Newton, Leibniz, all these people, they too had issues. Not that I'm comparing myself to Newton and Leibniz, of course, but I thought I should be open about it. Okay, I'm sort of in the process of mourning. Okay, so this week is about the fundamental theorem of calculus, but we still have a couple things to discuss before we get to that. Problem set 8 is up already. There's a bunch of it's all about Riemann integration. So this time, I hope you're going to appreciate the way I wrote the problems, because there was one problem. It was like Riemann integrability is equivalent to these 10 billion different things. I separated that into 3 different problems. So it's going to be more manageable, I hope, this time. So that's that. And then next week, on Friday, we're going to have our second midterm. Now, depending on how we go, we might excise some of the topics that were scheduled to be discussed on week 11, next week. So for instance, this Cauchy principal value business, and even improper integrals. They're important things, of course, even for applications, but we might not have time. We'll see. Okay. Are there any questions before I start? Okay. You don't need to be somber. Okay. So we have the closed and bounded interval as usual. The point of proper or definite integrals and improper integrals is that when you switch over to improper integrals, you start looking at functions defined on sort of like unbounded domains, perhaps. For instance, if you want to do something like the Laplace transform. Anyway, so last week, or the week before, on Friday, we were discussing this theorem, and I had messed up the proof of one part of this theorem, which says that if I have a Riemann integrable function f, then its absolute value, so the function that takes the value, absolute value of f of x at x, itself is Riemann integrable. And furthermore, their integrals are related this way. So the idea is, of course, that if you can integrate, if this thing makes sense, if you were to put absolute values to it, and if you were to put the absolute values inside, that bound would possibly grow. Why? Because initially this function could have negative values and stuff like that. So maybe my function is like this. Imagine. It's a square wave, you would say. And so certainly, if this is 1 minus 1, 1/2, 1, this is an integrable function. Its integral is 0. So the left-hand side here would be 0, whereas the right-hand side would be just 1, right? Because the absolute value function is just the function that is constantly 1. Okay, so we had done this, assuming the first part, but we need to show the first part, okay? So I'm going to do the first part, and we're going to use this exercise. Namely that if I have two numbers a and b, then this relation holds. Namely, the absolute value of the difference of the absolute values is bounded from above by the absolute value of the distance. And this really is not about real numbers, it's about metrics in general. Namely that any metric, d, is Lipschitz relative to itself. There's a couple of different ways of interpreting this, but they all are true. Okay. So, and this also is called sometimes the reverse triangular inequality. Okay, so I'm going to use this exercise. Okay, so let me let P, curly P, be a partition. What I want to do is, so my mistake last time was that I was trying to handle the lower Darboux sum of f in absolute value. But really, when it comes to integrability of a function, I should be trying to control the gap between the upper Darboux sum and the lower Darboux sum. Okay, that's the idea. And indeed, the claim will be that the gap between the upper and lower Darboux sums of f in absolute value is bounded from above by the gap for f itself. And so here's what we can do. Maybe I can just start with 1 pixel. And let me let 2 points in P. Okay. So certainly I have that f of x is bounded from above by the sup of f restricted to P. And likewise, bounded from below by the inf. That's by definition. But I can apply the same thing to y. But let me write it like this with a minus. In which case, here I would have the minus inf. And here I would have minus sup. Which means that if I were to add these up, I have that the difference between f of x and f of y is bounded from above by sup of f restricted to P minus inf of f restricted to P. In here I have minus the same number. Okay. I'm just using the definitions of inf and sup. But of course, this means that, now note, first of all, this is a non-negative number because sup is always greater than or equal to inf. And I'm saying that this quantity is bounded from above by this non-negative number and from below by its negative, which means that this value, in absolute value, is bounded from above by this guy. I'm just going over this slowly because this is sort of like a review if you want. And I had messed it up as well. So, good so far? Now, this guy itself bounds the difference between the absolute values, you see? So here, I use the exercise. Let me say here exercise prime. So this first exercise, if I use a equals f of x and b equals f of y, I get that. But of course, the absolute value of any number is greater than or equal to the number itself, which means that if I get rid of these absolute values over here, I would have that f of x in absolute value minus f of y in absolute value is like this. Ultimately, I have that for any x and y in P, it is the case that the distance between, or rather the difference of the absolute values is bounded by this. Now, in this expression then, if I were to optimize, in other words, if I were to look at the soup over all x's like this would possibly grow, but I'm saying that this guy, which doesn't depend on x, is an upper bound. Which means that I can replace this by the soup, and likewise I can replace this by the inf. So soup of f in absolute value restricted to the pixel p minus inf of f in absolute value restricted to p is bounded from above by soup of f restricted to p minus inf of f restricted to p. And this is what I wanted. Any questions so far?
How did you bound the f of x minus f of y by an absolute value?
Yeah, so hang on. Which one are you saying?
When you put the absolute values around f of x and f of y.
Oh. Do you agree that this, so you're asking about this?
No, I'm asking about the first one.
Oh, this one?
How you put the absolute values around.
Oh, okay. So from this step to this step. Well, I'm saying, look. So this is a, let's say, A. Okay. Let's call this B. This is also B. Okay. But A being bounded between B and minus B is literally the same thing, or it's equivalent to A in absolute value being bounded by B. B being a non-negative number. If you want, you can think of this as saying also A that satisfies this is the same thing as saying that A is in the ball centered at the origin of radius B, for instance. Okay, yeah. Any other questions so far? Why did I try to get this? Because I am assuming that f is Riemann integrable, ultimately expressions of this form I'm going to have some control over, right? So this is basically the gap of f for f restricted to this pixel p. Sometimes you might also see the word oscillation, which in a previous problem set you sort of like took pixels smaller and smaller, and you looked at that how that oscillation sort of like changed over time, and that sort of turned out to be equivalent to continuity somehow. It's sort of like a similar idea, really. But the point is that now if I were to look at the gap between the upper and lower Darboux sums relative to this pixelation, okay, so that bounds the same pixelation, or rather the same gap, but for f in absolute value. So let me continue here. So from here, so now I'm looking at the gap for f in absolute value using this pixelation. But this is a finite sum of expressions of the form, well, let me not write it. I'm going to add over all pixels this expression. So this is the proxy for the height information times the length of the pixel. Okay? But this is saying that if I were to go from here to there, this gap would possibly increase. So I have this. Okay, now we can use one of the characterizations of Riemann integrability. One of them says that f is Riemann integrable if and only if there's a sequence of partitions such that the gap converges to 0, right? So since f is Riemann integrable on I, there's a sequence of partitions such that the gap converges to 0. But then again, I can use the same sequence of partitions, which would say that by the squeeze theorem, because this is always non-negative after all, the same sequence would give me gaps converging for f in absolute value. And that's the end. I apologize for messing this up earlier. I just got confused about, soups and nymphs. Nothing too sophisticated, as you see. Basically, just we're using definitions of soup and nymph. Any questions about this? Okay, so here's a mean value theorem using Riemann integrals. There are actually two different versions of the mean value theorem, but we have access to only one of them right now. Once we cover the fundamental theorem of calculus, which probably is going to be tomorrow, we're going to have another version of the mean value theorem. But hopefully this will also give some sense as to why it is called the mean value theorem, okay? Yeah, let me write it there. It goes like this. So mean in math also stands for average, okay? And this is why it is called the mean value theorem. Of it, average. So when people are talking about on average this and this happens, they really mean, or in mean this happens, blah, blah, blah. They mean the same thing. Another word for this is expectation or expected value. They're all pretty much the same idea. And it says this: if I have a continuous function on the closed and bounded interval I, then, in fact, f realizes its average. In other words, there is an x star such that f of x star equals the integral of f, except it has to be normalized, so you need to normalize it by the length. Okay. So this right-hand side you would call the average of f on I. So in a sense, so I also said that this is also called the expected value. Or expectation. It turns out, so this is a number, okay? It turns out that if you consider this number as a constant function, this particular constant function is the constant function that best approximates f. So out of all constant functions, this constant function is the best approximation for f. So it is its expected value. Okay, there's a formal statement behind this, but it's going to take some time to write it out. Maybe in the next problem set you're going to see it, because it's a very useful idea. Okay, so any guesses as to how to handle this? We have a bunch of like theorems about continuous functions defined on closed and bounded intervals. We have basically three, right? One of them is the maximum principle. It says that any continuous function on any closed and bounded interval attains its max and min. Second, it is that, what does it say? Yeah, so the image, I guess we have four theorems actually. The image of an interval under a continuous function itself is an interval. Third, we have the intermediate value theorem. Fourth, I guess that's about like strictly increasing functions. So we have three theorems: intermediate value theorem, maximum principle, and the image of an interval under a continuous function is continuous. Okay. So any guesses as to how we can sort of come up with this x star?
Well, we know it's probably between, well, we know it's in the interval. It's probably, the f of the x star is probably between the, well, not probably, it is between the supremum of f on the interval and the infimum of f on the interval.
Yes.
It's going to be between those. Then we can probably prove that x star is there by the intermediate value theorem. No guarantees on how to find it, though.
So your colleague is suggesting the following. If you can show that the right-hand side, this average, is in the image, then by the intermediate value theorem, we can guarantee that there's a point where f actuates this value. That's what we want. But how do you realize that this guy is in the image? Well, you cannot take the derivative yet, right? So if we had sort of like some differentiability and stuff like that, we have another mean value theorem. We're going to discuss that later. The subtlety here is that I'm not saying that this x star is going to be in the interior. Maybe it's in the boundary. Mean value theorem always gives a point in between, right? But here, maybe this x star is the left-hand point. Okay, but that's a good start. Oh, by the way, let's also remind ourselves, we had discussed how a continuous function is integrable. So this makes sense, really, okay? So if I were to take an x and I, then f of x is bounded from above by the max of f. By the maximum principle, maximum of f exists. It's a number. It's a finite number. And likewise, here's the min. But then I can think of this number as a constant function. Constant functions are integrable, okay? Which means that if I were to take the integrals of all of these, the same inequalities would hold. But if I'm just integrating a constant function, this is nothing but min of f times the length. And this is nothing but max of f times the length. Which means that if I were to divide everything by length of I, the average would be between min and max. So 1 over L of I, integral of f is in the closed interval whose endpoints are min and max of f, which of course is nothing but the image of f. By the intermediate value theorem, I know that there's a point where f attains this value, yeah. So you see, once you sort of like think of the statement in just the right way, it just like falls out from the definitions. Of course, the real art is to realize that, oh, you know, this is something that I can use in this situation. Okay? So we have so far built certain like tools. One of them is the intermediate value theorem, maximum principle, blah, blah, blah. And then I look at the statement and I'm trying to sort of reverse engineer it. How can I sort of like come up with something that ends with this? So I start from the end, and I backtrack a little bit. Okay. Any questions? Okay. What do I want to do? There's one theorem. Oh, by the way, this in the textbook is written, but it's not proved. It was an exercise, but I thought it would be good to discuss it. Okay. So now we're going to do something slightly different. Okay. So far, when we looked at this expression for the integral, we had always fixed this domain over which we're integrating. Okay. Now we want to say something about what happens if we change the domain. And in the problem set 8, you're going to see sort of like a situation, a problem where you're taking limits as this interval sort of like grows. Okay. Certainly, I would want to have something like this. If I have an integrable function here, right, and if I cut it in half, certainly this part should be integrable, this part should be integrable, and the integral should add up to the original integral. So we need to prove this. It is true, of course. If it weren't true, then there was something fundamental wrong with our formalism. And later on, if you take the sequel class, you're going to sort of like generalize this idea. And you're going to start saying the following. Somehow, there's a space where intervals live. Instead of intervals, you're going to call them one cycles. And then you're going to call this expression a one form. And you're going to say, oh, I'm just pairing this one cycle with this one form. That gives me a number. So this is going to be in the sequel class. For now, we're just looking at the single variable case. And so this formalism of differential forms also simplifies a lot of these more advanced fundamental theorems of calculus, higher dimensional, like the Stokes theorem, divergence theorem, all that stuff. So, yeah, let's do this. I'm taking a midpoint in the interval, which is I. Then I'm going to be fast a little bit because it takes a while to write this down. I'm thinking of lower integration as a certain function on the set of all bounded functions, right? So you feed to this expression one bounded function, it gives you the lower integral. But you have these two as well. And I'm saying that given any function f, I can take the complete lower integral on lambda to rho. That's a number that always exists. And if this were mu, instead of looking at the whole integral, lower integral, I can look at the lower integral coming from this piece and the lower integral coming from this piece, and they should add up. Okay? That's what this is. And of course, the same thing should hold for upper integrals. Maybe I should remind you what this lower integral was defined as. So recall, this is the soup of all lower Darboux sums where the partition varies on over IP, over the interval partitions. So you do some sort of like a minimax if you want, right? Because this lower integral involves an inf, so you do minimax here. And if you do maximin, or I guess you should say maximin, and if you do the other way around, then you get the upper integral. So maybe I should write it. So soup over this. So this lower integral was this guy. You do inf and then soup. And then you do it the other way around. And that gives you the upper integral. Inf over partitions. And then upper Riemann sum. Upper Riemann sum itself involves soups. So this is just inf sum soup. Okay. This is like a very common theme in math and many different fields where you have to sort of like, you end up needing to sort of optimize things, get sort of like the specific value. You do this minimax or maximin type of stuff to get the nice value. And so this is about the lower integrals. Same thing holds for the upper integrals. Third, a function is Riemann integrable on I if and only if its restrictions to these subintervals themselves are Riemann integrable. So this notion of Riemann integrability descends, if you want, to subintervals. And likewise, if you were to take two Riemann integrable functions, you can glue them together to get a larger Riemann integrable function. And fourth, of course, the Riemann integrals add up. Lambda to rho equals lambda to mu plus mu to rho on the set of all Riemann integrable functions. Also recall that this was an exercise that I had left to you, that the set of Riemann integrable functions is a vector space. In other words, if you were to take two Riemann integrable functions, their sum itself is Riemann integrable, and a constant multiple of a Riemann integrable function, 2, is Riemann integrable. Furthermore, this Riemann integral operation that takes a function, sends it to its integral, is a linear transformation. It's not necessarily a matrix, but it satisfies the axioms for a function, a functional, being linear. Any questions about this? Okay. Let's first start with 1. Maybe I should mention this. It looks complicated, but the main complication is to open up the definitions, because this involves a minimax, and so you need to open up the definition so that everything sort of becomes explicit. And of course, the proof of 2 is very similar to the proof of 1, so I'm going to skip that. So this is an exercise. Let's start with the proof of 1. Here's the idea. So I'm sort of thinking back about the definitions. This involves a soup over partitions of lower sums, right? So let me just fix a partition. So I'm going to try to work with partitions here. I want to relate partitions of this larger interval to partitions of these two guys, and vice versa. So for instance, if I had one partition for this left side and one partition for this right side, by putting them together, that gives me a partition for the larger interval. Okay, so that's the first piece. Right. Then I can, so these are collections of subsets. I can take their union. This is going to be a partition of I, and certainly the lower integral of f relative to this union partition is going to be the sum of the corresponding lower integrals. Right, because here's the picture. So here's lambda, here's rho, somewhere here is mu. P, curly P, is a pixelation of the left side, and curly Q is a pixelation of the right side. This is P. Somewhere here is Q. Okay, so if I were to think of them together, that itself gives me a pixelation of the whole thing. And of course, this lower Darboux sum over this whole pixelation is the sum of this pixel, the sum of the lower Darboux sum coming from this, and the sum of the lower and the lower Darboux sum coming from this. Any questions about this? Okay. Well, so this guy, because I know that f is, oh, I don't know that f is integrable, but still, I know that this is bounded from above by the lower Riemann integral, by definition. But then if I were to optimize this guy and that guy separately, this would give me the lower integral of f over the left interval. And then likewise, if I were to do the same thing here, that would give me the lower integral over the right piece. Okay, so this is one side of the statement. I need equality. I showed one side. If I can show the other way around, I would have equality. Any questions about this so far? Okay. For the other side, I'm going to start with a partition of the larger interval and somehow try to get partitions of smaller intervals. So let me continue here. So this was this side. Oh, sorry. No, it is correct. That side. And then for this side, if I were to take a partition of the larger interval, how can I get pixelations or partitions of smaller intervals? So here's lambda rho, and I have a pixelation R. Something has to be done here, right? Because I cannot just rewind this argument over here because I don't know if one of these cut points exactly matches with this midpoint mu. But what I can do is I can refine my partition R by adding that one additional point if needed. Okay? So somewhere here perhaps. So let me define R star to be the common refinement of R together with this partition. Okay, this was the common refinement, recall. Now this guy can be written as the union of one P and one Q. P being a partition of the left interval and Q being a partition of the right interval. Oh, I have them already. So this I can write as union Q, P an interval partition of lambda to mu, and Q an interval partition of mu to rho. So I'm just saying, okay, so once I add this extra point, midpoint that I have to have, that was given to me. This pixelation here gives me P. It's a pixelation of lambda to mu. And this pixelation here is Q. It's a pixelation of the right interval. Okay? So, I don't want to erase this. Let me erase this part. So I'm continuing from here. The lower Darboux sum of f relative to the partition that I started with is bounded from above by the lower Darboux sum of f relative to r star. Recall this was something that we had proved. If you refine your partition, lower Darboux sums increase. That's why you're taking sup over all lower Darboux sums to get the lower integral. So this is going to possibly increase. But then this is equal to the lower Darboux sums coming from P plus Q. Okay. Now, previously, when we were doing the other way around, we first took the sup over partitions of the larger interval first, and then we took sups over partitions of the smaller interval. Now, for the other way around, we're going to do it the other way around, right? So, if I were to optimize over P, yes. So this is bounded by this, and this guy is bounded by this. But then I'm saying that for any r, lower Darboux sum of f is bounded from above by this expression, which means that the sup over these guys has to be bounded from above by this. Which is the other way around. I would highly recommend that you go through the same proof for the proof of 2. It's basically the same idea. And in the textbook too, they prove this, but I didn't like the proof presented in the textbook that much. This is just like a first principles proof, if you want. Any questions about this? Yes.
This is more of a notation question.
Yes.
Is the partition product symbol, is that like a capital pi?
Yeah, exactly. Yeah, this is a pi, capital pi. Yeah. Like capital sigma? Yeah. Any other questions? Tomorrow we're going to have to do these. I don't want to start today because it's going to take some time. So I guess that's it for today, and I'll see you tomorrow. Thank you. Okay, let's start. Good morning. Lots of snow today. I walk here and I saw a bunch of tree branches and stuff falling down. And in fact, one of them fell down as I was walking. It's kind of crazy. But yeah, I don't think it's going to stay. It was already like slush when I was walking. Anyway, so today we're going to do the fundamental theorems of calculus. But before that, we had to we need to finish this the proof of this theorem. So we had done the first part last time. So this is the interval additivity of lower integrals. And similarly, there's also the interval additivity of upper integrals, of course. So this I had done last time. This I had given as an exercise. Third item is the most complicated one. We're going to have to spend some time on this. It says that a function is integrable on I if and only if its components, its restrictions are integrable. So that means that if you have a function on a large interval, you can restrict it to a smaller interval that's still going to be integrable, and vice versa. We can start from this side. If you have one function here that is integrable, some other function here that is also integrable, then you can join them together to get a function that is integrable. Of course, the values of the left function and the right function should match at the very least in this midpoint. And then the fourth item is that on the set of Riemann integrable functions on I, the linear transformations that are this integral on the one hand and the sum of these two integrals on the other hand, they coincide as linear transformations. Now, let me immediately state also that once we have 3, 4 is going to follow immediately. Recall that we had this other statement that if f is integrable, then so is f in absolute value. And then we had this inequality. The second, this part sort of was immediate, more or less, but this we had to spend some time on. And similar thing holds in the situation as well. Once we can sort of verify the integrability of the functions themselves, then item 4 follows immediately, because I know that this transformation on R really is the lower integral, right? Because that's how this is defined. We have this guy, lower integral, upper integral, and we're defining this insofar as these two are the same. And of course, this set is defined to be the set of all those functions where these two operators coincide. So let me just summarize this. Proof of 4, assuming 3. So maybe I can just say for f, a Riemann integrable function, recall that Riemann integrable functions are by definition bounded. So this is a certain subset, vector subspace if you want, of the set of bounded functions. Well, this, if you want, this is the same thing as the lower integral. But then this, by part 1, let's say, I can split lambda to mu f of x dx plus lower integral from mu to rho f of x dx. But I'm assuming item 3. I'm assuming that if I'm taking an f that is integrable, then its restrictions are integrable, which means that, again, by definition, this expression is the same thing as the integral without the underscore, underbar. And so here I'm using 3. So the proof of 4, assuming 3, is straightforward. If I wanted, I could have used number 2, of course, instead of using number 1. I could have used the upper integrals. Any questions about this? Okay, So now we need to work on number 3. Okay, I'm going to erase this. So this is an if and only if statement, which means that we need to show the equivalence. That is to say, I need to assume f is integrable, and I need to show that any of its restrictions is integrable also, and vice versa. I need to assume that these two guys are integrable, the restrictions, and I need to show that I can glue them back together to get a larger integrable function. Okay. Let's see. One side is easier here. I think the gluing part is easier. Let me have a look. Oh yeah, okay. Yeah, so this way, the backwards direction is easier. Let's do that first. I'm assuming that f is some bounded function on I such that its restrictions are Riemann integrable. Lambda to mu, this is Riemann integrable on the interval lambda to mu, and f restricted to mu to rho is Riemann integrable on the interval mu to rho. I want to show that f is Riemann integrable, right? By definition, this means that I want to show that the lower integral of f equals to the upper integral of f. Recall that this lower integral was the soup of all lower Darboux sums, where you're varying the partition, and the upper integral was the nth of all upper Darboux sums. So any ideas, any guesses as to how I can do this?
My thought would be when you're looking at partitions, you could just fix a partition at mu. And then, I'm sure that I think that would be easier.
Well, we can use step 1, for instance, right? So this guy, so f is a bounded function because I started like that. By 1, this is the same thing as lambda to mu integral of f. After this class, I'm never writing integrals again. This is by 1. But I'm assuming that, so the restriction of f to this interval is integrable, which means that I can take this lower bar and put it as an upper bar. That's the definition of f restricted to this interval being integrable. And likewise for this. But then I can use item 2 to combine them back together. Okay? So assuming that the pieces are integrable, I can put them back together to get the Riemann integrable function. Going forward, meaning assuming f is integrable and then showing that one of its restrictions, it's slightly more tricky. It's not too complicated, but still. Any questions, though, before I get to that? Okay. So let me leave it here. Let me erase this part. Now I need to show that if I have an integrable function, well, let me just try to show that this is integrable. In fact, in the next problem set 8, you're going to see a problem where you're going to need this idea that if you have a Riemann integrable function, then any of its restrictions to a closed and bounded interval is itself Riemann integrable. And then you're going to take the limits over the interval somehow. Okay. So this side. Say I have a Riemann integrable function on I. Let's just show that the first restriction is integrable. Let me just leave it like this. The other side is analogous, but it's a nice exercise. I'm just going to leave it to you. It's the same idea, of course. Okay. So we have a bunch of different characterizations of Riemann integrability. Here, for instance, I used the characterization, basically the definition, right? I just showed that the lower integral is equal to the upper integral. That's the definition of Riemann integrability that we first discussed. But one of the characterizations is that if I can find a sequence of partitions of this guy such that the gap between the upper and lower integrals, or upper and lower Darboux sums of this guy, relative to that sequence of partitions, converges to 0. So it suffices to find a sequence, maybe let's call it P, of interval partitions of lambda to mu, such that the limit as n goes to infinity of u of f comma pn minus L of f comma pn goes to 0. Well, I know that a similar sequence exists for f. Right? That's a characterization. Let me say R bullet be a sequence of partitions such that the limit as n goes to infinity u of f comma r sub n minus L of r comma L of f comma r sub n goes to 0. This exists because I'm assuming that f is Riemann integrable. And so here's the picture. I have my larger interval here, and then I have my partition. It partitions the bigger interval. This is I. So here's my R sub n. Okay. The heuristic, of course, is that as you're increasing R, the pixel size should shrink to 0. Right? Now, I sort of used a similar trick before. Here, there's an issue, because one of these cut points, so it may fail that one of these cut points is this midpoint that I want. But I can refine R sub n using this partition to get some other partition. The gap relative to that refinement sequence 2 converges to 0. And so based on that, I can do something. Okay? So put R sub n star to be R sub n refined by lambda to mu and mu to rho. Okay? But then if this is the case, I can write this refinement as P sub n union Q sub n, where P sub n is the left part of the partition and Q sub n is the right part of the partition. So here I'm going to call this P sub n, this Q sub n. P sub n is a partition of lambda to mu, and Q sub n is a partition of mu to rho. Okay? So let me look at the gap between the upper and lower Darboux sums of f relative to this P sub n. Okay, so this is what I wanted, recall. So if I can bound this gap by something that I know decays, then I'll be good. And indeed, we can do this because of the following. Okay. Now what I can do is, right, so this is the sum over all pixels in the partition P sub n of sup of f minus inf of f. To that, if I add the sum over pixels coming from Q sub n, that sum can only increase. It cannot decrease. But then this is the same thing as this guy minus this. But then R sub n star refines R sub n, which means that the upper Darboux sum here relative to R star is less than or equal to the upper Darboux sum relative to R sub n. And likewise, this has to increase, which means that this is bounded by this. But then I assume that this goes to 0, which means that by squeeze, this has to go to 0. So I was able to produce a partition of the left interval such that the gap relative to that partition, that sequence of partitions, converges to 0. And of course, the proof of this exercise is to use this Q sub n. Okay? Any questions about this? So this idea of common refinement is a very convenient one. And problem set 8.2, you're going to need to use it. Because so one of the characterizations of Riemann integrability is saying something about the pixel size, really. It says that for any epsilon, there is a delta such that for any partition, such that each of its pixels are of length at most delta, then the Riemann sum is bounded or is epsilon close to some fixed value. So there you're going to have to play this common refinement game a little bit. Okay. So now we can switch to the fundamental theorem of calculus. So this is the basics of Riemann integrals. There are many more stuff, of course, but and first let me define this thing called the signed definite integral. So far, this integral, that Riemann integral that we were looking into, was the unsigned definite integral. So this lambda to rho x is the unsigned definite Riemann integral. Of f on the interval lambda to rho. And I told you that when you look at this from a physical point of view, you should think of something like mass. Okay? So F is something like density. You have a rod, I, with endpoints lambda to rho, and you're computing its mass. So this is like mass. Sign integral is more like work. Okay? So the difference between mass and something like a mass quantity and work quantity is that this is my function f. It doesn't matter for the unsigned integral how you're sort of like computing the area underneath. Okay? In other words, you can go this way or you can go this way. This is what you would say is an orientation. Okay? So the interval in one-dimensional objects admit two kinds of orientations. Either you go one way or the other way around. Okay? And so how you're counting this should not matter. And in the notation, this is signified by well, basically just using this interval without a specific orientation. But if you have work, if you're thinking about work. Okay. So counting or looking at the work from here to there is very different from looking at the work going from here to there. Okay. And so the signed definite integral, so for f Riemann integrable on I, let me put it this way perhaps, and alpha and beta in I the signed integral, signed Riemann integral, of f from alpha to beta. See, I have a direction now. I didn't say that alpha is to the left of beta here, and that's on purpose. This is defined like so. Now we're using the standard calculus notation. This is basically the unsigned Riemann integral up to a sign, okay? It just, when it comes to computations, it becomes an issue, but in abstract, it doesn't seem that sophisticated or complicated. Oh, it's a plus. F of x dx. It's the unsigned integral if alpha is to the left of beta. If alpha is to the right of beta, then, well, you again look at the unsigned integral, but you put a minus in front. Okay. In one dimensions, it doesn't seem that complicated, but in higher dimensions, this is something that you end up needing to understand at a more deeper level. Because in higher dimensions, you have, maybe I can draw something like this. You have sort of like a surface, let's say. And so it becomes important when you're trying to compute some integrals, surface integrals and stuff, how you're orienting this, right? So it's like either you're going to use the right-hand rule, which means that this should be the orientation, or you're going to use the left-hand rule. Or if you have sort of like a ball or something, and you're trying to sort of like compute the flux of some fluid out of that ball, obviously it matters in which direction you're computing things. It's going to be either inward or outward, right? So in higher dimensions, this really becomes important. And in the sequel class, you're going to spend, I hope, some time discussing this in more detail. In one dimensions, it's just a matter of sign here. Okay, so let's do an example before going into the fundamental theorem of calculus. So the fundamental theorem of calculus basically relates integrals and derivatives, right? So far, we didn't do anything about differentiation and integration. We were just looking at integrability. We said that, oh, continuous functions are integrable. Not all integrable functions are continuous, and so on. But we didn't say much about differentiable functions. Of course, differentiable functions themselves are continuous, which means that differentiable functions are integrable. But we want to go beyond that. So here's an example. I'm going to let I to be the interval -1 to 1. And let me let f of x to be defined like so. Well, let me send it to 1 for negative x values and -1 for positive x values. If x is less than or equal to 0 and -1 otherwise. So if you think about the graph of this function looks like so. It's a square wave, if you want. That's a function f. Now, is this function integrable? Yeah, right? Because how could you argue about this? Well, you could say there's a couple different ways of doing this, but one way to do this is that a function is integrable if and only if its restrictions are integrable. But certainly, the restriction of f to the left side is a constant function. Constant functions are integrable. And likewise, the restriction of f to the right side, right side is integrable. And so f has to be integrable by the previous theorem that we did. So that's one thing you can do. Oh, maybe I should mention here, so this should be signed and definite. There's another word, indefinite integral. Indefinite integral is the same thing as antiderivative. Let me write that as well. So that's why these are called definite integrals. So indefinite integral means you have the plus c, that is like anonymous. They are related, of course. All of these are related. Antiderivative. And really, the fundamental theorem of calculus relates this indefinite integrals to the definite integrals. Now, here's the next question. Does f have an antiderivative? Is there a function, some other function g, such that g prime equals f? This is basically solving a differential equation, if you want. So, question. Does f have an antiderivative? So what do I need? I need a function some other function g. So g such that g prime equals f. So this is an example of a differential equation. You're given an f, you want to solve for g. Okay? Well, what do I know about this g? I know its slope, the graph of its slope, right? So on this box, let's think about this. This is the same box, -1 to 1. Okay. Now, on the right side, the slope, right, f is the slope, is -1. Which means that g must be like this. Of course, you don't quite know where exactly this is happening, but somewhere it has to be like so. And likewise, on the left side, it has to have slope 45 degrees, pi over 2, right? Because here the slope is 1, here the slope is -1. Okay? So I know that if a g exists, it must be the case that g prime of x equals 1 if x is negative, and minus 1 if x is positive. Okay. Well, we know that any function whose derivative is a constant function has to be a degree 1 polynomial. This is one of the previous problem sets, which means that g of x has to be x plus, let's say, a if x is non-positive. And likewise, it has to be minus x plus b if x is positive. Okay. So we're getting somewhere. So you see, I have the slopes, but I don't know the y-intercepts. Right. But here's the problem. So I hope you can see this. This is an important point. So now, here a and b are arbitrary. Any choice of a and b gives me 1g such that g prime equals f. But of course, there's a problem because at this intersection point, something bizarre is happening. Right? So really, this is sort of like a differential equations way of doing it. But now that we know formalisms, this is not quite true, right? This is true, or rather, this is true as you're away from 0. So you should be writing it like this. But here's the problem again. If I wanted, I could have chosen a and b such that this piece matches up with this piece, so that this becomes a continuous function. But you see, even if I could do that, at that point, this g is not going to be differentiable. No matter which a and b I choose, g, which came from this, has to be non-differentiable at the origin, at 0. There's going to be a kink there. Either it's going to be discontinuous, but even if it were continuous, it's going to be non-smooth. Okay? So, for instance, as I'm varying a, what does this mean? I have the left side, and I know that it has to stay like this, because this is y equals x, plus a constant. Okay? And so, as I'm converging to x equals 0, this is going to be sort of like the situation. As a increases, this left side sort of like goes up, and as a decreases, it goes down, again with the same slope. The slope is 1, but the constant changes. If I were to do the same thing with the other side, now the slope is this way, and changing b changes the height. Okay? So as an exercise, put this on Desmos and sort of like let the variables change, see how the graph changes. Desmos this. How many of you have heard of Desmos before? Okay, all of you. So yeah, most of you. So this is like a graphing calculator. It's pretty convenient. You can just put in sort of like parameters and stuff like that. The point I'm making is that, for instance, maybe I chose, let's say that I chose both a and b to be 0. Okay? If a were 0, then this would be the left side. And if b were 0, this would be the right side. But certainly this is not differentiable. It is differentiable everywhere except at the origin. Okay? Now, how can I sort of relate to the continuity properties of f? You see, this function fails to be differentiable exactly where f fails to be continuous. It's actually going to be the other way around. one part of the fundamental theorem of calculus is going to say that if I have a Riemann integrable function f, then I can look at one of its antiderivatives, and it's not going to be quite an antiderivative, because when you say antiderivative, you really want g to be differentiable everywhere. But there is a sort of there's a substitute for this antiderivative business, and the fundamental theorem says that this substitute for the antiderivative is differentiable at any point the original function f is continuous. Okay. Any questions about this? This is one of the important points of this class, so that's why I want to sort of take some time before getting into the formalism.
Could you kind of explain that again? I'm kind of confused why we don't need to worry about it, I guess.
Worry about what?
It not being differentiable at that point. Like, we can still totally use it just fine.
Well, I mean, so when people give you an equation like this, given f, find me a g such that g prime equals f.
Right.
Without any qualifications, they want this g prime to be valid, defined everywhere. Okay? Now, but if sometimes it doesn't happen, and then you sort of interpret this in a weaker sense.
Okay.
Okay? You can do that. So I can say, okay, I want to solve this, except at bad points. Okay, so you can say, okay, so this guy, f, jumps, there's a jump discontinuity here, which means that I shouldn't be able to find this g prime at that point. But at any other point, I can try finding it. And in fact, one of the previous problems from problem sets, from the problem set, says that, well, the derivative of any differentiable function satisfies the intermediate value property. So you could immediately sort of conclude that there is no g that satisfies this. Because if there were, that would mean that g is differentiable such that its derivative doesn't satisfy the intermediate value property. Okay? So you can sort of justify it like this as well. But this is sort of like a more hands-on approach. Of course, you can. In this case, we have a specific example, so we can solve everything. And maybe I should be a little bit more clear. We're going to spend more time on this, but the substitute for this antiderivative is going to be the following. For instance, I can look at the following. This is perhaps kind of bizarre, but you probably saw this in the single variable calculus class. I'm going to come up with a function where the variable is, well, one of the endpoints here. Okay? It's not going to be quite a g like this because of this discontinuity issues and stuff like that, but we're going to get to that later. So the substitute for g is going to be capital F of x from -1 to x f of t dt. How many of you have seen something like this before? Okay, some of you have. This is kind of weird because the variable of the function I'm defining is one of the endpoints of the Riemann integral. But the point is that this is always well defined. That's a good point. Because f is integrable on any subinterval, it too is integrable, which means that this is a number. This is a well-defined function. Okay? Now, whether or not this is differentiable, it's a different matter. Okay? Yes?
How you make Desmos do indefinite integrals because it doesn't like support those out the box.
Oh, really?
It's yeah. This is generally how I would do it because like it always wants you to put bounds on your.
Oh, yeah.
It's not a computer algebra system.
Oh, that's interesting because it can support f prime.
Yeah, it does support f prime, which is kind of strange.
Well, I mean,
it's so
it's a
so
different.
It's so powerful. You could probably program a computer algebra system in it.
Yeah.
Sorry, I interrupted you.
Oh, no, it's good. It's an interesting question. Someone should try to implement a computer inside Desmos.
It should be possible.
Well, yeah, I've seen someone do a 3D ray tracing in Desmos. It's kind of crazy. But anyway, we're going to continue this tomorrow. I want to sort of like compute this guy, for instance, for this example. But then maybe I want to look at this other guy. What if I were to take the midpoint? There's nothing here that is really saying that I should be studying the integral from -1. And when x is negative, that means this is a signed integral. Okay, so these are signed integrals. And in a sense, perhaps this is more natural of a choice because so there is sort of like a center here. And so you want to see what is happening when you're going to the left and to the right. Okay, we're going to discuss these tomorrow. Thank you. Okay, let's start. Good morning. So today I'd like to start talking about the fundamental theorem of calculus, proving them and stuff. But it really is confusing, the statements and stuff like that. And most confusion comes from different types of integration. We have the indefinite integral, we have the signed definite integral, we have the unsigned definite integral, and so on. And this makes things complicated a little bit. So before stating the theorems, there are two fundamental theorems. I would like to discuss this example more in detail. And this should tell you really something, right? Because usually I just like go ahead and discuss the formalism and abstract stuff. But really this is important to understand. So I want to sort of prepare you for what is to come. So this was the function that we were looking at, okay? I have the interval -1 to 1, and f is a function defined on I taking real values. And it's a piecewise defined function, and I'm defining it so that f of x equals 1 if x is negative, so it is this part, and it is -1 if x is non-negative. Okay, so this you might call a square wave. It's like goes like this, and you may want to sort of like extend it periodically. That's what you would do, for instance, in more applied situations. But let's just look at this sort of basic part of it. First question. We had talked about this yesterday, but I want to go over it again. Is f Riemann integrable? The answer is yes. How can you say this? Well, you can compute the lower and upper Darboux sums and use the definition. That's one way. Another way would be to say that, oh, this function is made up of two pieces. Okay, one piece is this part, the other piece is this part, and this left restriction of f is a constant function. Constant functions are Riemann integrable. So the left part is integrable, and likewise, the right part is integrable. And if you glue two integrable functions together, you get an integrable function. That's another way of saying that this is integrable. Third way of showing that it is integrable is to realize that this is a monotone function. It is non-increasing after all. As you're going from here to there, the value of f never increases. It can decrease or can stay constant. And monotone functions are integrable, which we discussed that before also. So this is three ways of verifying that f is Riemann integrable. Okay. Any questions about this so far? I'm just like trying to bring all the theory back in. By the way, I'm going to take attendance today. Okay. So yes. Question 2. Is f continuous? Certainly not. It has a jump discontinuity. Of course, you can take the limit, right? Like the problem is 0. And for continuity, so when I'm saying f is continuous, I'm not saying f is continuous like pretty much at any point, right? Like there's no quantifiers or qualifiers. If it's, so in order for f to be continuous, it has to be continuous everywhere. No. So what you can say is this. We can read into the question a little bit. It is continuous everywhere except at 0. So even though it is not continuous, it is what you would say continuous almost everywhere, if you want. That's a technical term that we're not going to discuss in this class, but if you take further analysis classes, you're going to sort of spend a lot of time what it means for something to happen almost everywhere, or with probability 1. So set of bad points for f is very restricted, okay? Question 3, does f have an antiderivative? So antiderivative is the same thing as an indefinite integral. AKA some other function that is defined everywhere that is differentiable whose derivative equals f. A differentiable g, so is there a differentiable g such that for any x, okay, so it has to be differentiable everywhere, and for any x, g prime of x has to be equal to f of x. Okay? So in differential equations terminology, this f function will be your forcing function, and you would try to solve this equation for g. G would be the solution. You're saying, does this differential equation have a solution g? Okay? Any guesses as to the answer to 2, 3? Yeah. No, we had discussed this also. You can argue about this in multiple ways, but one way to argue about it is to say that argue by contradiction. Suppose there is a g that is differentiable everywhere, whose derivative equals f everywhere. If that were the case, then I know that g prime, by one of the problem sets, has to satisfy the intermediate value property, but clearly f, which is supposed to be g prime, doesn't satisfy this property. So there can be no such g. Okay? No. Questions about this so far? Now, like I did in question 2, I want to read into it, okay? Because, so there are multiple ways of doing math, okay? One way of doing math is to interpret everything in a very formal manner, and then someone asks you a question, and then the answer is either yes or no, and then you're done. That's how you would try to answer a question in the exam, for instance. Okay, because you're short on time and all that stuff. But there's another way of doing math, which is where you sort of like start perturbing the question, right? Like this was something that we've been discussing all along, because there is no end to math, okay? So once you have no as an answer to a question, well, you start changing this a little bit, okay? You say, okay, if this has no solution, then can I sort of like weaken this restriction? Can I ask for a function g that is maybe not differentiable everywhere, but differentiable at most points? And whenever the derivative exists, it is equal to f of x. So now you're sort of relaxing what you're asking. You're asking for something less, okay? So, okay, did we all sign this, the attendance sheet? No, but, Now I want to discuss that, what comes after this. And another point here is that people who apply math, people like engineers, electrical engineers and so on, for them, they would not take no as an answer in this situation. Because this f it's a certain like quantity, it shows up in experiments and blah, blah, blah. And it's a certain sort of physical quantity. And maybe it's like the, okay, I don't remember the names, but they have certain sort of quantities as current and blah, blah, blah. For instance, if you're doing electrical engineering. And it turns out that you have a wave and you want to be able to come up with an antiderivative. Even if there is no formal antiderivative, like I'm asking in Math 3210 in this formal math class, still, if the answer is no, what is the next best thing? Okay? And so, one thing I can do is the following. For any three numbers, I can define G, which is going to depend on these three numbers as parameters. Take x to, well, a bunch of points, okay? It's going to be a piecewise defined function. The point is that the bad situation, so the reason why this question is unanswerable is this gap. But if I were to just restrict myself to this left side, I would have a very nice answer, because on the left side, f is 1, and so an antiderivative, if it existed, would have to be x, right? The antiderivative of this is x, plus some constant that I don't know, x plus a. And again, on the right side, I don't know what, so on the right side, this antiderivative, if it existed, would have to be minus x plus some constant that is quite possibly different from this constant, right? It could happen. So let's say c. Maybe just to be consistent, let's call that b, because yesterday I said b to that. And in the middle, I don't really have any information whatsoever. I can just use some arbitrary number c. Now this is a piecewise differentiable function. Okay, in particular it is integrable, but that's not what we're looking into. Is piecewise differentiable. This is continuous if and only if A equals B equals C. So G, ABC is continuous if and only if A equals B equals C, in which case, of course, I get something like this. So somewhere here, perhaps. So this is G if I were to choose A equals B equals C equals 0. But if I were to choose some other number, some other value for this common value, maybe 1, then that would be shifted. Okay? And furthermore, you see everywhere except at this problematic point, G is differentiable and its derivative equals f. G, A, B, C is not differentiable at 0. It is differentiable everywhere else, no matter what you choose as A, B, C. But it's differentiable for any x in I take away 0, and g prime of ABC of x equals f of x. Okay? So I cannot solve this equation. That's too restrictive. But if I were to allow some random behavior, some bizarre behavior at this problematic point, then I can solve the equation. Okay? So in a sense, in differential equations language, you would say that GABC, this family of functions that depend on 3 numbers, is the so-called general solution to this equation on a subset. Okay? Now, the problem with this is that in this case, I could just look at the function and focus on these partial definitions and just integrate, because this is just a constant function. And I know how to take the antiderivatives of constant functions. But in practice, there are more complicated functions. So somehow we need another way, more robust way of handling this. And it turns out that there are many functions whose antiderivatives are basically impossible to guess using nice functions that you learned in single variable calculus. Okay, that show up in sort of applications. Any questions about this so far? So this generalized answer to question 3 I could come up with based on the specific example that we had. But now I'm going to do something that looks more bizarre, but that's going to work for more general integrable functions. Okay? So let's do this. Now I'm assuming that I can't sort of guess this antiderivative, at least partially. And I'm going to try to use the integrals. I know that f is integrable, which means that I can integrate it. And in fact, I can integrate it on any subinterval. And that's the key observation. I'm going to integrate f on different subintervals. And as I vary the boundary of the interval, that's going to give me a function. Okay? So consider this. Capital F, take x to, let's say, 0 to x, f of t dt. Okay? Now here I'm using the signed integral. Okay, so this is the signed integral. Signed Riemann integral. Right, so this is a signed integral of f from 0 to x. But I'm not saying that x is to the right of 0. Possibly it is to the left of 0. Okay? So explicitly, if you wanted to write it, let's also remind ourselves. I would write it like this. F of x equals the integral from 0 to x. So this is the case when x is to the right of 0. And if it is to the left of 0, then I cannot write 0 to x, so I'm going to have to write x to 0. But I'm going to put a minus to denote that I'm going in the other direction. So explicitly, this symbol means just this. And so these are unsigned Riemann integrals. Okay. So this guy, and this guy. Okay? We were dealing with unsigned Riemann integrals, and then yesterday I defined a signed integral in terms of unsigned Riemann integrals. Any questions about this so far? Now, is this well defined? Well, yes, because of one of the theorems that we did yesterday, which says that if f is integrable, which it is, on this, of course, in this case, I could just explicitly write things down, but I'm trying to not use the specific properties of this example. If f is integrable on I, then it is integrable on this subinterval also, okay? So this makes perfect sense. And likewise this. I should ask, so here, okay, does this expression depend on t? Once you integrate, so t is supposed to be a dummy variable. This is not a function of t. Once you integrate something relative to a variable, you don't have dependency relative to itself, or relative to that variable. It depends on t, it depends on x, it doesn't depend on t. Okay? Any questions about this? Now let's compute this in this situation. Somehow, ultimately, it should give me something like GABC. That's my expectation, but we have to compute it. Well, okay. So, computation. I'm going to have to look at the two cases. Either x is non-negative or x is negative, because the definitions are different. The sign is going to be sort of like important. Like in abstract math, it's not that important. And even sort of like when it comes to abstract situations, people would say modulo sign, what I'm saying is correct, and they wouldn't worry too much about it. But when it comes to applications, plus is very different from minus, okay? So it's important to keep track of these kind of things. So I have two situations. If x is non-negative, then f here is just -1. I'm gonna do this explicitly this time because this is important. Okay, I can just substitute in this integral, instead of f of t, just -1. Okay, and in the other integral, now x is to the left, which means that f of t is going to be +1. Okay, so this is just an integral of the constant function -1 from 0 to x, so on the interval 0 to x. So what is this? This is just this constant times the length. So this is just -1 times x if x is non-negative. And in this case, what is the length of this interval? X is a negative number. Okay? It gets confusing. So you see, x is negative, so the length is the right endpoint minus the left endpoint. So the length of this interval is -x, because x is a negative number. But I have an extra minus here. So I have minus 1 times -x. And so this is -x if x is non-negative, and plus x if x is negative. Okay? And so somehow this operation, this bizarre thing that we did with having the variable in the boundary of the integral, picked out G0, 0, 0. Okay? And of course, what is happening here geometrically, so for instance, when x is 1/2, you look at the signed area underneath the graph of f, and so it's this. Okay? The signed area underneath is minus x, minus because it's below the horizontal axis. And if x were negative, you get the signed area again. In this case, it is positive. Okay? Questions about this? This is the theorem to learn from this class. So I just want you to be very comfortable with this idea. And I hope this example is going to sort of help you sort of orient yourself when you start getting confused about the abstractions and stuff.
Would I be right in saying this would be largely the same for something like a jump discontinuity? Just sort of
What do you mean?
be on both sides, downwards.
What do you mean?
I guess if you had a different type of discontinuity, it's still a lot of this logic would follow, right?
Maybe. I don't know. Yeah. I don't want to say something wrong, so.
Right.
Yeah.
Depends, I guess.
Yeah. Yeah. I would need to think about it. I mean, what does sort of like stop me from answering something like that is that maybe integrability sort of restricts the type of discontinuities you can have and stuff. So I don't know it off the top of my head, so I don't want to answer. But any other questions about this part? Okay. So somehow, another way of saying this is that if I'm trying to find an antiderivative, in this case, I can't find it, but this integration with one of the bounds, the variable, picks out one solution, conditional solution, in the sense that this G0, 0, 0 doesn't solve this everywhere, but it solves it wherever it can, right? So it's the next best thing. Now I'm going to leave it to you as an exercise to compute the following guy, okay? Go through the calculations again. So exercise. I'm going to define a G. It's going to be the same, except that I'm going to anchor it to a different base point. Let's say that I'm anchoring it to -1. Compute this guy explicitly. Again, you're going to see that it's going to be a G, A, B, C for some A, B, and C. Okay, so then G equals for some ABC. Do this explicitly. This is an important exercise. I should mention, so if I were to take any other base point, okay, and I can go through the same stuff, and I hope at this point you're convinced that, again, this antiderivative, or rather this integration, is going to give you one of these GABCs that I had decided, that I had guessed before. The interesting fact is going to be that whenever you have an integrable function like this, and whenever you look at an expression of this form, the resulting function is going to be continuous. In other words, in another situation, if you were to come up with G, A, B, C in this form for some capital G, then A has to be equal to B and B has to be equal to C. So for any, let's say, gamma in I, I'm going to denote by F sub gamma to be the function defined like so. Then there's a unique, let's say, A, such that F sub gamma equals G sub A, A, A. In other words, while this method works for arbitrary integrable functions, in this specific example where I know my function, lowercase f, where I could, yes, all possible sort of conditional solutions to this, this method is not going to generate for you the general solution. Okay? Some of them it's going to miss because the outcome is always continuous. Questions about this? Okay, so now let's state the theorems. There are two fundamental theorems of calculus. I don't know why one is called the first and the other one is called second, but I'm just going to follow the textbook. So the first fundamental theorem of calculus is about the integral of a derivative. And then the second one is going to be about the derivative of the integral. So as usual, I have I closed and bounded interval from lambda to rho. And I'm going to take an integrable function. Oh, I have 4 items, so let me write it like that. So for any f, Riemann integrable, and for any capital F, antiderivative of f, well, the unsigned integral of f on the interval equals f of rho minus f of lambda. That's the first part. Second, I want to say something similar, but for signed integrals. And for any alpha and beta in I, I'm not saying that alpha is to the left of beta. Maybe it's maybe their orders are switched, but I'm going to use a signed integral this time. So I'm looking at the integral from alpha to beta, and I'm allowing beta to be to the left of alpha. But it doesn't matter, it turns out. This is always this guy minus this guy. Signed integral is always from alpha to beta. If alpha is to the left, then that means that integration is to the right. And if alpha is to the right, then that means that the integration is to the left. In any event, the right-hand side is always at the value at the endpoint minus the value at the initial point. Okay. Third, if I have a C1 function, these are just restatements of the same thing, really, but I like to sort of write down sort of different statements for the same thing. So for any C1 function, continuously differentiable, what did I write? Yeah. The unsigned integral of its derivative is g of lambda minus g of, g of rho minus g of lambda. And fourth, for any g in C1, and for any two alpha and beta, the signed integral from alpha to beta of g prime is g of beta minus g of alpha. Any questions about this? Now I should mention, based on our previous example, just because a function is Riemann integrable, it doesn't mean that it has an antiderivative. Okay? If f is a Riemann integrable function that has no antiderivative, that means that this statement doesn't say anything. I'm not saying that it has to have an antiderivative, but it says that if it has an antiderivative, then this formula has to hold. That's an important point. Riemann integrable doesn't mean it has an antiderivative. In other words, that it has an indefinite integral. It's a definite integral, but not necessarily indefinite. Not exist. Okay? But if it exists, it has to satisfy the formula. Questions about this? And why am I calling this the integral of derivative? Because it's easy to say, and it's like, so if capital F is an antiderivative of f, lowercase f, then lowercase f is a derivative of uppercase f. So first you're differentiating, and then you're integrating. That's how I'm thinking about. That's how I sort of keep it in mind. I want to say one more thing about this. So this is coming from, again, this from the world of topology. But whenever you have a subset, you have what is called the boundary of the subset in a metric space, let's say. I'm not going to give the definition, but let me just say that in the case of intervals, the boundary is just the endpoints. But it turns out that if you have an orientation, as we have in the case of signed integrals, then the boundary too has an orientation. So boundary operator. And in an evocative manner, this is denoted by partial sign. Okay? And so I have this line segment here, let's say from alpha to beta, and it is oriented. It goes from alpha to beta. Okay? Its boundary is the set of 2 points, and they are oriented this way. This point is oriented this way, and this point is oriented in the backwards direction. let's just take this as a definition. This is a consequence of the definition of the boundary operator, but let's not worry about that. I'm just trying to give you some intuition. But also, if I were to look at, for instance, this guy, alpha to beta, but pointing in the wrong direction, in the backward direction, its boundary again will be the same. Okay? And so, for instance, item 3, I can write like this. Or maybe item 4, let's say. So this is a sine integral. I'm writing this left-hand side in a bizarre manner, but this is sort of more symbolic. I'm saying that the derivative of the function integrated over the whole thing is the function itself integrated over the boundary of the thing. So you can put the partial inside the integral or in the sort of like domain variable if you want. Okay, of course, in this case, what this means is that evaluate the function at beta with a positive orientation, so that's the plus, and then evaluate the function at alpha, but that has the minus orientation, so you need to have a minus in front of it. Okay.
This is Stokes.
Yes, it's leading to Stokes. And if you take the SQL class, what you're going to do is you're going to want to integrate likewise functions that are multivariable. And then you're going to have a function, for instance, defined on this region R, and then it's going to have a boundary. This curve that encircles the region. And then you're going to say that R, so the integral of the derivative over the bulk is the integral of the function over the boundary. This is Stokes' fundamental theorem of calculus, whatever. Okay? There's like, you're going to see 5 different sort of reincarnations of this idea. This is one of the most important sort of ideas of math. And typically, you take an arbitrary discipline of math, there is a fundamental theorem of calculus like this. Maybe it's not even about calculus, okay? Maybe they use like different words for these things, but it's ultimately just this. Maybe they say homology, whatever. In physics, I think, this is what they call a bulk and boundary principle. Okay. Questions about this? Okay, let's prove it then. I'm only going to do one. The other ones actually follow from one, okay? I'm going to leave that to you. I just wanted to write these different items down because when I was first learning this stuff, somehow this statement was hard for me to keep in mind. This antiderivative capital F and blah, blah, blah. Sometimes I feel like, somehow I feel like this is the easiest way to keep in mind. And also, item 1 is the one that was given in the textbook too. So, exercise 2, 3, and 4, assuming 1. Proof of 1. Okay. So, you see, when it comes to proofs related to Riemann integration, things get messy because you end up needing to use all this technical stuff about lower and upper Darboux sums and so on to handle things. Okay, so let me start with a partition. I'm going to try to do something about this. Let curly p be an interval partition. Let me fix a pixel. And let me let 2 points in this pixel. Is that what I want? Let me see. Oh, I guess I don't need these 2 points. Let me do it like this. P, by definition, this pixel is a closed and bounded interval. So let me denote it by lambda sub p, rho sub p. It has a left endpoint, it's the min, right? So minimum of p, and rho sub p is the maximum of p. Okay. Now, capital F is differentiable because it's the antiderivative of some other thing. And let's just assume that my pixel has positive length, right? It's like, let's not use the same point. That is to say, let's say that lambda sub p is strictly less than rho sub p. Now what can I use here? I have a differentiable function and 2 distinct points. Mean value theorem. Okay. What does it say? It says that there's some point strictly between here, in particular it has to be in this pixel, such that f prime at that value is the rise over run. There's an S of p inside p such that f prime at S of p is capital F at rho sub p minus capital F at lambda sub p divided by rho sub p minus lambda sub p. Okay. So here's my pixel. I applied the mean value theorem to this, and it gave me 1 point like this. Of course, this is evocative because this is supposed to be a sampling function. I'm going to use that as a sampling function. And you see, capital F prime is nothing but lowercase f by assumption. And this guy is nothing but the length of the pixel p. So I can write it like so. Solving for this, this is just, okay. This is just lowercase f evaluated at S of p times the length of p. But I can do this for each pixel of my partition, which means that if I were to look at the Riemann sum of lowercase f relative to this partition and this specific sampling function, right? This is the sum over all expressions of this form. Well, I can replace this by this. Now, what is the last step here? I guess we have 2 steps. But first, perhaps I should mention that we can write this. This sum really is nothing but f of rho minus f of lambda. So this particular Riemann sum of lowercase f equals this right-hand side. Okay? Now, why is that the case? Well, ultimately, it's because this sum has a bunch of like terms that cancel out. Okay? I guess we're out of time, so I'm not going to continue this. But we're going to talk about this more on Friday. Thank you. Okay, let's start. Good morning. So we have a lot to cover today, fundamental theorems of calculus. We had started talking about the proof of the first fundamental theorem. I just wrote the first item. Remember, we had 3 more items that I gave as an exercise. They just like follow from this. So we're going to do lots of interesting stuff. So I'm going to be taking attendance today. So let's remind ourselves what we were doing. I'm going to try to be a little bit more sort of, I'm going to try to use slightly better notation perhaps in this situation. So here's what we did with the proof of this. The idea basically is that because I know that capital F is differentiable, given any partition, I'm going to use mean value theorem on each pixel of the partition that I chose for F. And so that sort of relates F to its derivative. So let's say that given a partition P, let's say that the pixels of P are like this. So lambda to x1, x1 to x2, xn minus 2 to xn minus 1, and then finally I have xn minus 1 to rho. Okay, that should be a 1. Where let's say that lambda is x sub 0 to have consistency. And then let's call rho x sub n. So these are the cut points that determine the partition. Okay. By mean value theorem, applied to F on one of these pixels, for each I have S of P of I inside P sub I. So this is, for instance, P sub 1. No. I say this is P sub 1. This is P sub 2, and so on. So I have n pixels. Here. So I, which is xi minus 1 to xi, such that capital F prime evaluated at this point is the rise over run. So capital F of xi minus capital F of xi minus 1 divided by xi minus xi minus 1. Okay? But of course, this capital F is nothing but capital F prime is nothing but lowercase f, and this denominator is nothing but the length of the ith pixel. So I can write it like this. The point is that if I try to write a certain Riemann sum for the integrable function that I started with, lowercase f, this Riemann sum is going to consist of sums over terms of this form. And so P comma S will be the sum over these expressions. But then each of these I can replace by this guy. But then this is a finite sum. I can split this. This is a sum where I goes from 1 to n minus the sum where I goes from 0 to n minus 1. Which means that out of this expression, only the last term is going to survive this. And then I'm going to have to subtract from it the first term of this. But of course, x sub n I had defined as the right hand point, and x sub 0 I had defined as the left hand point. Okay. Any questions about this so far? This we had discussed on Wednesday. I just wanted to repeat. So somehow, this first fundamental theorem of calculus, you should really think of mean value theorem applied many times. We're not done with the proof, but we're almost there. So this means that given any partition, I can find a sampling function S, which is this function generated by the mean value theorem. It's not an explicit construction, of course. Mean value theorem just tells me the existence of something. And relative to this sampling function, this particular Riemann sum becomes exactly equal to the right-hand side in what I'm trying to prove. It should be the other way around, of course. Okay, well, if that is the case, I know that the lower Darboux sum of f relative to this partition lower bounds this expression, and likewise the upper Darboux sum upper bounds the expression. Like this. Okay? Now, this expression, this set of inequalities, hold for any partition P whatsoever. And the partition dependency is only on the bounds. Now, if I were to optimize this left side, that has to converge to the lower integral. And if I were to optimize this, it has to converge to the upper integral. But I had started with f integrable to begin with, in which case lower integral equals to the upper integral, which is equal to the integral. Okay? Which means that if I were to optimize over all partitions, this is going to turn into the integral of f, and likewise this too is going to turn into the integral of f, which is a finite number. The only way I can have a value between the same value is that that value is the same. And that's what I wanted. So the mechanism really is that. So what is going on here? So the way I think about it is it's sort of like a bunch of like dominoes. You sort of like kick, or prod one of them, the one on the left, and then everything sort of trickles down, and you get the force on the right-hand side. That's sort of the idea. Any questions about this? Okay. Now, before stating the second fundamental theorem, I would like to discuss the key item that we're going to use in the second fundamental theorem. Did we all sign the attendance? Okay. Not many people today. Okay. So I'm going to fix a Riemann integrable function, and I'm going to look at its signed integrals, where I'm going to leave the endpoints variable. I really want to sort of understand how this signed integral with endpoints variable vary according to the change of the endpoints. Given, so let's call this a theorem. Let me let f to be an integrable function and define I'm going to define a family of functions. Okay? And this I'm going to denote by this. Capital F sub bullet, it's not a sequence necessarily, but that's where the parameter is going to go. Okay? Takes a point in the interval as a parameter and produces a function on the interval. So it's a function of functions, if you want. And so, given any gamma, it's going to send it to the function that takes an x and sends it to the signed integral. Of f. In other words, f sub gamma of x is nothing but this integral. And let me remind you, this is the signed integral, so I'm not saying anything about whether or not x is to the right or to the left of gamma, which means that this really means this. It is the unsigned integral from gamma to x of f of t if x is to the right of gamma and minus the unsigned integral from x to gamma of f otherwise. The second fundamental theorem is going to be about this family of functions. Now, we had discussed how, earlier this week, how this is something like a substitute for an antiderivative. The antiderivative of f may not exist in general, but this is the next best thing, okay? And the second fundamental theorem is going to be about the properties of this function. of this family of functions rather. Any questions about how this is defined? So it's kind of bizarre, but this is a function whose inputs are interval points, whose outputs are functions on the interval. Okay? So you need to take a gamma, send it to some function that takes an x, that sends it to somewhere. If I wanted, I could have written this as a multivariable function, but this is, I think, better to write this way. Now, I want to understand certain properties of this. And the theorem is this. Oh, maybe I should also mention that this is always well-defined, okay, by something that we proved earlier this week. Given any integrable function, that function is also integrable on any subinterval, okay? And so this expression makes sense. In order for this to make sense, we had proved that f restricted to this interval with endpoints gamma and x is integrable, and this value is a well-defined expression. Okay. Now this is going to be lots of fun. And this is an instance where from analysis sort of emerges algebra somehow. Then, for any alpha number, f sub alpha of alpha is 0. For any alpha and beta, in I, f sub alpha of beta plus f sub beta of alpha is 0. And for any alpha, beta, and gamma, f sub alpha of beta plus f sub beta of gamma plus f sub gamma of alpha is 0. And I hope you're starting to see the pattern. If I were to take n many different, possibly different points, and add them up in this fashion, I should be getting 0. Alpha sub n minus 1 evaluated at alpha sub n plus f sub alpha sub n at alpha sub 1 is 0. Of course, item 4 is the general statement, right? It's like for any n and for any n tuples of numbers, I have this property. Okay, I'm going to leave 4 to you as an exercise, but I'm going to do the first 3. Somehow, to get 4, you're going to have to do some sort of induction probably. Now let's start with item 1. F sub alpha of alpha is 0 for any alpha. Well, looking at the definition, this is nothing but the integral of f from alpha to itself, alpha to alpha. What can its value be? Can it be anything but 0? Right? Because you're sort of integrating over one point. No matter how you think about this, this ultimately should involve some sort of Riemann integration. So you're going to have to take Riemann sums or lower Darboux sum, upper Darboux sum, whatever. But all of them involve something about the length of the pixel, right? But there's only one pixel here, and it has length 0. which means that this has to be 0, basically by definition. Any questions about this? This is something silly to say, but for completion purposes, I decided to state it. Now let's do 2. Well, this, by definition, is the integral from alpha to beta of f. But of course, this is the same thing, but the endpoints switched. Well, so this is the integral from alpha to beta. And so this is the same integral, but backwards, right? So this guy is the same integration, but this way. Well, that means that by definition then, this has to be minus beta to alpha, which means that this is minus f sub beta of alpha. In other words, if I were to take this to the other side, this plus this would have to add up to 0. There's nothing very deep going on really, but somehow this is very fundamental. That's why I'm sort of taking my time, okay? Certainly not the most complicated thing that we've ever discussed, but turns out to be very important. Any questions about item 2? So somehow the picture then is that we have 2 points, and if you look at the expression from alpha to beta, and then from beta to alpha, they cancel out, okay? This is some sort of a conservation law. You sort of integrate over a loop, and things add up to 0 ultimately, okay? This is like a very abstract version of a conservation law, in a sense of physics, perhaps. So let's do 3. There's probably a slicker way of doing this, but I want to be explicit here, okay? So this is the main idea, but I'm going to leave it to you to formalize it. So exercise, formalize. I have 3 points, alpha, beta, and gamma in my interval. Well, I need to figure out in which order they are positioned, because if they are ordered in the correct fashion, we had already proved this. We proved a version of this for unsigned integrals. The problem is that these are signed integrals. And so, in how many different ways can I list these down? Well, there are 6, right? 3 times 2 times 1. So there are 6 options. They're positioned like this, but maybe like this. Or maybe beta is first and then alpha and then gamma, or maybe beta is first and then gamma and then alpha, and then gamma, alpha, beta, gamma, beta, alpha. These are all possibilities. There are no other possibilities. Okay, so maybe I should be explicit here. Somewhere here is lambda, here's rho, here's lambda, here's rho, here's lambda, here's rho, and so on. Okay? So, let's first start with this situation. So, I'm always going to start with integrals from alpha to beta, then from beta to gamma, right? So, integral from alpha to beta plus integral from beta to gamma, and then I'm going to integrate from gamma to alpha. And so, look what happens here. Alpha to beta, beta to gamma. By the additivity property for unsigned integrals, I know that the sum of these two integrals add up to the unsigned integral from here to there. Which means that if I were to go in the backwards direction, they're going to cancel out. Okay? And then alpha to beta, beta to gamma, gamma to alpha. Alpha to beta, beta to gamma, gamma to alpha. Alpha to beta, beta to gamma. You get the point. Okay? So these are all closed loops somehow. And over closed loops, this function, this family of functions, they add up to 0. Okay? So if you want to be more formal about this, you would write everything down, and based on each of these properties, each of these configurations, you would reduce the signed integrals to unsigned integrals and sort of use the additivity property for unsigned integrals to sort of get the expressions. But underneath all that, it's as simple as this. In more complicated situations, what ends up happening is that this capital F it's something that is defined in a more bizarre fashion, and it's not as clear what type of loops you should be looking at. Okay? In this case, they are sort of loops in a rather intuitive sense. Questions about this?
Not super related to this, but well, I guess yes, related to this, but not related to what we're learning about it. This notion of like loops on this seems like very interesting.
Mm-hmm. Yeah.
Because there's like these subsets where it's going in one direction and a relatively sensible loop.
Mm-hmm.
Well, I guess they're all doing that. But like for 4 elements, there's going to be a bunch of really weird loops.
Yes, that is true. Yes, but there's going to be some cancellations, hopefully. Yeah. That's the point. So for this, you would probably want to do induction. Yeah. Let's say that for any loop over, I did the base step if you want. Say for any loop with n points, the statement holds. If you were to add one more point, how are you going to reduce it to the previous situation? Okay? So you want to start with a loop with n plus 1 sort of points, and then you're going to have to reduce it to somehow. You're going to have to come up with a loop with n many different things. Yeah. Okay. Now, it turns out the abstract definition that sort of like encapsulates this idea of adding up to 0 over loops is the third property. Somehow, if you have 3 points where something like this holds, that's sufficient for a lot of different things. And so this has a specific name. This is what is called the cocycle property. And in fact, in one of the previous problem sets, you proved another cocycle property. That was in the context of derivatives of the iterates of a function. So let me write it over here. Recall that we had the following. So I had in a previous problem set, we had this. We had a differentiable function, and then we defined this j function, right? Given any integer and a point, you iterate f n times, you compose it with itself, and then you differentiate it once relative to x. Okay? So this is what is called a discrete time dynamical system. Somehow, the idea here is that f models how a certain sort of closed system changes in time. It is discrete because each iteration of f represents one time step. Okay? And so the formula was, this is the thing that you proved. So at time n plus m, if I were to look at this Jacobian, that's the name of this. This is the same thing as this guy. And so where's the loop here? Okay? The loop is here. I start at an initial condition, initial point x, go forward using my function f m times, so that now I'm at f to the m of x. And then I can go further to f to the n plus m of x. So in m time, I'm starting from this initial condition and go over here. And if I start here, in further n times, I'm going to go over here. Okay? But of course, instead of doing this in 2 steps, I can do it in 1 step. And so that's my loop. And then you think about it, I can sort of put this to the other side or something. It looks a little bit more complicated compared to this expression over here, but it's the same idea. Okay? So over my dynamical system, if I sort of look at a loop like this, loop in time perhaps, then this j function has to go to 0, has to become 0. Okay? So this is yet another cocycle. Okay? So this notion of a cocycle is a lot more general than I'm making it sound like. Any questions about this? Okay, let's state the second fundamental theorem then. The second fundamental theorem is going to be about these f sub gammas. Now, the first fundamental theorem was about the integral of derivative. The second fundamental theorem is about the integral of the derivative of the integral. Okay. I'm going to have 4 items again. And I'm going to start with an integrable function. So let f be Riemann integrable. Let me have space. Then, for any gamma, f sub gamma, this function that I defined using the integral, it's not necessarily differentiable, but it's the next best thing. In other words, it is Lipschitz. And furthermore, in fact, its Lipschitz constant is bounded by the sup of f. Okay, let me write here again what the definition of this f sub gamma was, just so that we can remember it. So here's a definition. Second item, for any gamma and for any x star in I, now this is about the differentiability of this capital F. If lowercase f happens to be continuous at x star, then capital F is differentiable at x star, and its derivative equals the value of lowercase f. If lowercase f is continuous at x star, then uppercase f sub gamma is differentiable at x star, and its derivative is equal to the value of f. Okay. Third, which is based on the second item, if more general or more specifically, if f is ck, k times differentiable, then capital F is going to be k plus 1 times differentiable. So for any k non-negative integer or infinity, and for any gamma, if lowercase f is in ck, k times differentiable with kth derivative continuous, then capital F is going to be ck plus 1, k plus 1 times differentiable, with the k plus first derivative continuous. And this guy is in ck plus 1. In particular, if lowercase f is c infinity, infinite to many times differentiable, this capital F is going to be likewise infinite to many times differentiable. And fourth is that if your lowercase f is continuous, then in fact this uppercase f happens to be an antiderivative. Now we talked about how a Riemann integrable function doesn't necessarily have an antiderivative, but if your function is continuous, any continuous function has an antiderivative. In the context of differential equations, this is called the existence theorem. So again, really the main parts are item 1 and 2. 3 follows from 2, and 4 follows from 3. And I'm going to leave 3 and 4 to you. So these are going to be exercises. Any questions about the statement? I should mention, of course, let's recap this as well. Lipschitz, in particular, means it is uniformly continuous, which means that it is continuous. Okay? Lipschitz is, of course, more. So. Okay, let's do the proof. So 1. So I fix a gamma, and I need to bound the difference of f sub gamma of x and f sub gamma of y for x and y arbitrary points. So now let's first do this. This is the expression I'm trying to bound. Okay. Now I'm going to use the cocycle property here, because you see cocycle property says the following. I'm going to use the cocycle property with the 3 points x, y, and gamma. So this tells me that f sub gamma of x plus f sub x of y plus f sub y of gamma equals 0. Okay? Now, let me isolate this guy. So okay. So this is one of my terms. And then if I were to put a minus, I would be able to switch gamma and y here. And then sending this to the other side, I have minus f sub x of y. But then again, I can flip the variables to get rid of this minus. Okay? Which means that this difference I can write as f sub y of x. What I'm trying to do is I'm trying to bound this absolute value. But this is the integral of lowercase f from y to x. Maybe y is to the right or to the left. But in any event, I'm going to be taking the absolute value. So I'm not going to see any minus. So I don't care about really the distance, whether or not y is to the right or to the left. This is going to be, let's say, like this, where j is the interval with endpoints x and y. If x is equal to y, then this is going to equal to 0, and there's nothing to do anyway. But this makes sense in any situation. And one of the things that we did before is that the absolute value of the integral is dominated by the integral of the absolute value, which means that I'm going to have this. It should be the sup of the absolute value of f. Then, so this is bounded by sup of f in absolute value times the length of this interval j, which has to equal to the distance between x and y. And this is what I wanted. You see, the sup of absolute value of f is a constant c such that the Lipschitz property holds. Okay. And since the Lipschitz constant of a function is the best c such that the Lipschitz property holds, the Lipschitz constant of this has to be bounded from above by this. And in fact, I do think that this has to be equal, but I think that is correct, but I didn't have time to check it. Okay. So this capital F sub gamma need not be differentiable, but it is the next best thing. It's a function that is Lipschitz with some control over the Lipschitz constant. Okay. Questions about this? Now in the textbook, there's like a perhaps more explicit proof, but you see, it's very convenient to use this algebra property. We just looked at the definition of something and we came up with an algebraic property, basically. It sort of simplified a lot of the situation, a lot of the argument. And in fact, in the second item too, I'm going to use the same thing. Now I'm assuming that lowercase f is continuous at this x star. I need to show that uppercase f is differentiable at x star. You see, uppercase f is something like the integral. I'm differentiating the integral here. And I want to show that that derivative at that point is equal to the value of lowercase f. So I need to show this. I'm just going to open up the definition, take the appropriate limit, and show that it converges to this. So 1 over h of f of x star plus h sub gamma this is the rise over run expression for capital F. I want this guy to converge to lowercase f of x star as h goes to 0. So I'm trying to bound this guy. Okay, again by the cocycle property, I can write this expression like this. Okay, I'm going to have to get more space. Now I have two situations, either h is positive or h is negative. Let me just assume, without loss of generality, h is positive. And this guy becomes this. So this is the integral from x star to x star plus h. But because I'm assuming that h is positive, that's really the unsigned integral. And here is the trick. I can imagine this guy to be 1 over h times the integral of this constant function over this interval. And combine things together to get this. That's with a plus, but if I were to put the absolute value inside, that would possibly increase. And so I would have here an absolute value. This is bounded by the sup of this function, but by continuity of f, I can make the sup as small as I want. So this is bounded by the sup of f of t minus f of x star in absolute value, where t varies between x star and x star plus h. For any epsilon, there is a delta such that for any h whose modulus is less than delta, this is bounded by epsilon, which means that this limit converges to 0. And that's the end of the proof. Okay, just in time. Thank you. Have a nice weekend. I'll see you on Monday.